How about a new topic? Let's talk about what I refer to as my infinite limits. Here's a pretty picture. I may not have done a good job with my drawing, but I meant for there to be a horizontal asymptote at y equals L, at least in the right-hand plane, and at y equals M, at least in the left-hand plane, for the graph of this equation. But what I want to do is create some rigorous definition that really pins down what it really means to say this is a horizontal asymptote. I think what it means is this, that the limit of f of x as x increases with that bound is equal to L. But then again, I need to know what that means. I simply think this is true if I have a horizontal asymptote with the right-hand plane, and vice versa. If I have a horizontal asymptote in the right-hand plane, this certainly is a true statement. But now to give rigorous meaning to this, look at my picture before I finish my sentence. If this really is true, then I think no matter how small of a positive number epsilon is, if this is true, then eventually there has to be some value of x, call it how about n, for which, if x is bigger than that big N, then my y values are within epsilon units of L. Let me say that one more time. This right here means, for all epsilon greater than 0, there exists an N such that the deviation between f of x and L in absolute values is no more than epsilon units whenever x is chosen sufficiently large. I can also rewrite that as an if-then statement. Sorry if my head was in the way. Here is a waste of 5 minutes of your life. I think these questions are silly. After all, you are a pre-calculus expert. The graph equation y equals this, or this, or this is the graph of a rational function. If the degree of the polynomial upstairs is less than the degree of the polynomial downstairs, if the degree on top is smaller than the degree on bottom of those polynomials, you get a horizontal asymptote for free at y equals 0. When the degree is the same, you get a horizontal asymptote at the equation y equals the ratio of leading coefficients. And if your numerator has a degree larger than the denominator, that means you have an oblique or slant asymptote. Well, that's what you're taught back in pre-calculus. Now let's prove it. Divide the limit of a rational expression. I will multiply top and bottom by 1 over x to a certain power. The power to which x will be raised is the highest power I see x being raised to in the denominator of that rational expression. Now, both in the numerator and denominator position, let me distribute the multiplication over the subtraction and the addition. But these three go to 0. And so I'm left with simply 0. Got the same answer I did back in pre-calculus, albeit you did not use this notation. Let's see if I can come up with that value using this new tool. Multiplying by a funky looking form of 1, which is 1 over x to some power divided by itself, where the power for x is the highest power I see x being raised in the denominator. But doesn't that give me this? But these two terms go to 0. And indeed, I am finally left with the ratio of leading coefficients. Thirdly, running out of room, so may I get rid of this? You know you have an oblique asymptote. So the y values are either going to increase or decrease that bound. To determine which, I'll play the same game. Multiplying by funky looking form of 1, which is something over something, where the something upstairs is 1 over x to the highest power you see downstairs, and here is the same thing. I will yet again distribute my multiplication. As I evaluate the limit, these two go to 0, and I'm left with this expression over 3, or the limit of that expression over 3, and this is going to increase that bound. Sorry, that really was a waste of time in the sense that I'm just using new notation to say the same old thing.